Alright, so we're going to have another look at the segment tree because I know it's been a stressful week, so let's have a recap of what we did. So our goal is to find the minimum range query from a left and right. So in this case we chose, well, what we're eventually going to do is do from index 4 to index 10. And so we built this thing called the segment tree, which is essentially you have every parent node has a range, and then each of the children take up half of the range, or approximately half the range. You try to divide it in half as best as you can. So if the node has a range L comma R, the left child will have a node range L comma half of mid and R. So we're just calling it mid, which was L plus R over 2. And then the right child is mid plus 1 comma R. So we bisect each of the sizes, and then we go through all the, and then we went through all the child. We went through each of the child nodes, kept dividing them in half and half and half until we got to a scenario where the left and right were the same, which we just assigned the value of the index in the array. So for example, 0, 0, the array at index 0 is 1, so we just put in 1. And then after we assign all the values to the child nodes, their minimum values are just the nodes, the values in the array themselves. We went back up in the tree, and we said, hey, are we going to take our left or our right as our minimum value? And then, for example, the range 0, 1, we divide by, you had a 1 and a 3 here. Obviously, 1 is less than 3, so you want to take the value from the left child, which is 1. And then we kept doing that, kept building up and up and up until we were at our root, until everything was built. And then this is the conclusion, and this is how we build our segment tree. So that's how we built it as a recap. Remember, the blue represents the minimum value, or the value in the index in the tree, and then the left and right are in squiggly brackets. But and everything is and so obviously every node has a left range, a left and right, and then an index. Now we have to actually figure out how do we do our query from a left and if we input a left and right, how do we do our query? And these were the cases. For a range QL, QR inclusive, the square brackets mean inclusive, meaning you include QL, then you go QL plus 1, QL plus 2, ... all the way to our QR. So for every for the query range QL to QR, and you're at a current node with the range its range L comma R, the thing inside the squiggly brackets in our tree. How do we figure out the minimum value in that case? So there's 3 cases that we came up with just before we decided to call it quits for the day. 1, the node's range left comma right is completely inside QL comma QR. In other words, like you see 6 comma 7 is complete. That says outside. My bad. Completely outside QL comma QR. So yeah, if for example you have a left and right of 6 comma 7, and then QL comma QR was 10 comma 11, for example, then what ends up happening is you return some dummy value as the minimum value. Like you don't want to actually have this influence the real minimum value, because none of the values in the range L comma R are actually included in QL comma QR. So you want to return a value so that it doesn't actually affect what your output is. So we're going to return some really huge number, which I just wrote as an infinity symbol. In reality, you can just return like 1,000,000 or something, because infinity obviously doesn't exist in C++. You could do return int max or return L long max, whatever you want. Just return some really large value for that specific query, because then you won't be including 6 comma, like 6, 7 will essentially be ignored because there's no way our minimum value is actually going to be some really huge number, given that L, R are under specific constraints. Okay, case 2. L, R is completely inside QL, QR. For example, our L, R is 3, 5, and then QL, QR is 0 to 8. Obviously, 3, 4, and 5 are all in between 0 to 8, so that means L, R is completely inside QL, QR. So, in this case, at the current query, you actually want to return the value that's stored in the node, because this is any of these three any of the numbers in this range or any of the indices in the range could potentially hold the minimum value. So you want to return the minimum value at that index, because we know that at every node in the tree, it's holding the left and right, but it's also holding the minimum values of all the children or all the values it's storing between the L, R indices inclusive. So you want to return the value at the node. And then not fully but partially intersecting ranges is our third case. Let's say, for example, our left, right was 3 to 5, and then we had a query range from 4 to 7. In this case, you don't know if the minimum value at that node is actually valid, like the 3, 5. Are you sure that's within the query range? If it was in 3, then you'd be returning, if you just return the minimum value at the query range and the minimum out of the 3 was 3, you'd be returning 3, which is not necessarily correct, because if that's actually lower than all the values in 4, 7, you're going to get an output of the value at 3, which doesn't work out. So you have to actually go into the children and go out of the 2 children and see, hey, where is, if I divide in half, if I'm going to 2 children, I'm bisecting the range that I'm looking at out of the 2 queries, and I can see which queries are valid. See, the 5, 5 is valid, so we could return that. But out of the 3, 4, we're still in an intersecting range. So that means I had to bisect it one more time to 3, 3 and 4, 4. Our 3, 3 is completely outside the range, so we return some really huge number. And then our 4, 4 is valid, so we return that value, and then we go back up and then say, our 3, 4, this is clearly going to be much bigger than the 4, 4 value, so that means I'm going to return the value that I got from 4, 4, and similarly, that would make our 3, 5 value less than, our 3, 5 value would be the minimum out of the 2 children, the values that you got from the function call, not necessarily the minimum out of the 2 children, because remember, this is including the node at index 3, which is outside the query range. Any questions up until then? So let's go ahead and actually visualize our 4, 10. Our query 4, 10 in our segment tree. Okay, so I'm going to use a different color. Let's go with green. Okay, so we want to call our query 4, 10. And the strategy for the first thing to do is to start at the root of the tree and then work your way down if we have to, using the cases that we developed down here. So if that seems really if the cases seem really confusing, how about we see an action first and then we see if it makes sense. Okay. So first we're at the root. Our L equals our L is 0 and our R is 11. And we have a query range 4 to 10 as our QL and QR. Now since here's the thing. Every element is all the QL, QR. Oh, I should probably add this as a case. I thought it was more intuitive at first, but Okay, let's have a look to start off, and then we'll build the case itself. If we have a query from 4, 10 with nodes from 0 to 11, we see that all the values 4, 5, 6, 7, 8, 9, 10 are in the range 0, 11. However, not all values in the range 0, 11 are valid for our query 4 to 10 because the indices 0, 1, 2, 3, and 11 are outside of the range 4, 10. Whoops. So we actually have to treat this as an intersecting range because this has more values than we're looking for, and therefore if one of the values of 0, 1, 2, 3 or 11 are lower than our actual what we're supposed to output, then we're going to mess up and get a wrong answer. So that means we have to treat if QL, QR is complete inside L, R, then we have to treat it as an intersecting range. But remember, if the L, R is complete inside QL, QR, then we can treat it as L, R is inside QL, QR, and therefore we can just return the node's value. Okay, so let's start off. So we have a range 0, 11 for our left and right, and then QL, QR is 4 to 10. So is this an intersecting range? Is L, R completely inside QL, QR? Alright, so maybe it's better if I just show you the process of everything. Okay, so we're starting off. 0, 11, is that completely inside 4, 10? Of course not, because it's including the starting index is 0, while the starting index here is 4. So that means the indexes 0, 1, 2, 3 are outside of our query range. So we have to treat it as an intersection. So that means that we have to go from, we have to set the return value for that is going to be the minimum of the 2 return values that we get from our 2 children. So let's go to our left child first. 0, 5. And remember, our query range is 4 to 10. And still, once again, we have we still have 0. The starting index here is less than our starting index of QL. Or in other words, our L is less than our QL. Our left here is 0, and our left for the query range is 4. That means there are still some elements that are outside of the range QL, QR. So we have to go into and check each of the branches yet again for our minimum value here, which then we would return to our root node. And now we reach our 0, now let's go into 0, 2. And we see that this is completely outside the range 4 to 10. Because the right end is less than our starting query range. So that means we have to return some really high value so that it doesn't actually affect it. So let's just denote that with an infinity symbol. But in reality, it'll be like, let's say, 10 to the power of 9 or something like that. So the value we're going to return above is infinity. Now our range 3, 5. That's once again partially intersecting with 4, 10 because they're still including the element 3. So that means you have to go down into each of the roots, into each of the children and check, am I intersecting? And now we see that 5, 5 is completely inside 4 to 10, the range 4 to 10. So now we can just return 30. Return 30. And checking from the left, 3 to 4, that's still intersecting. And that's still intersecting, but not fully inside 4, 10 because we're still including the element 3. So we have to bisect, once again, check the children, and then return their minimum value. 3, 3 is now completely outside 4, 10. So now we have to return infinity. And then 4, 4 is completely inside 4, 10. So we return the node's value, which is 15. So that means the value 3, 4 in a query 3 comma 4 is either 15 or infinity, whichever one is lower. And since 15 is much lower than infinity, we have to return 15. Now between our value here 15 and our green value here 30 returned from our function at these respective nodes, 15 is less than 30, so I have to return 30. Now going back up one more, between infinity and 30 as our return value, oh, this is not 30, this is 15. I messed up. Because I clearly said 15 is less than 30, I just wrote 30. So our value here should be 15. Now between infinity and 15, 15 is less than infinity, so we have to return 15 for this one. And now we can't make any conclusions for our root node yet because we haven't done anything to the right side. So let's go ahead and do that. Oh gosh. Okay. Remember, we're still working with left and right for a query range 4 to 10. And then we have 6 to 11. And as we can see, this is only this is not fully inside 4 comma 10 because this is including the element 11. So that means we have to go and check the the values in the two nodes. And the range 6 comma 8 is completely inside 4 comma 10, so we can return the node's value, which is 16. Grab from there. And now we have to check the range 9 to 11 for our right child. And that value is, and that is only intersecting because you still have this 11 here ending. Whoops. You have an 11 ending here, but the query range ends at 10 on the right end. So that means you have to check the two children and return a minimum value from the query of those two. The range 9 to 10 is inside the range 4 to 10, so we can just return 6. But the range 11 to 11 is completely outside the range 4 to 10, so we return infinity here. Now, because we had 6 and infinity from our query ranges of the two children, that means the query for this node over here is the minimum of 6 comma infinity, which is obviously 6. And this makes this node over here, you had a 16 over here, and a 6 over here. So that means the query for the range 6 to 11, or for the range on 4 to 10 out of the right side, is the minimum of 16 and 6, which is obviously 6. And then now we can conclude from up here, 0 to 5, 6 to 11, we got a value of 15 from the left child and 6 from the right child. So that means our minimum value is 6. And since we started our query here, that means that the minimum value in the range 4 to 10 is 6. Now let's go ahead and verify that and make sure I didn't make a mistake. My computer loaded. Okay. Our value is 4 to 10. We have 15, 30, 45, 16, 18, 14, and 6. Clearly, 6 is the lowest element out of the range 4 to 10. So that means their return value has to be 6, which is the value that we got. Now, make sure you understand that the values I get from the function calls are the green values. They're not necessarily the values in that are stored in the node's minimum value, but it's the function's received minimum value because that's the value that we got. So let's go. So any questions about that first before we move on? All right. So remember when we start off that we said our root was from last week. Our root had an index of 1. We store our tree as an array with a root of index 1, and if any parent has an index of v, then our left child will have an index of v times 2, and our right child will have an index of v times 2 plus 1. This was demonstrated with the red here, giving us our indices. And as we saw before, it will guarantee that we won't have any intersections with, like you won't have any node that any two nodes that have the same index of the way we count it. And that can be proved by the fact that you keep dividing it 2. And the worst case scenario is you have 2 to the power something here, but then you have 1 more on the left side. So yeah, just always as our rule of thumb, if any node has an index v, say for example this has 5, that means our left child, if the node has children, the left child will have an index of v times 2, in other words 5 times 2, which is 10, and then our right child will have an index of 5 times 2 plus 1, which is 10 plus 1, which is 11. That's how we got 10 and 11 here. Okay, so let's go ahead and build our tree, and don't worry, I'll be posting all of this stuff in our resources, but let's go ahead and build our tree. Okay, so just to start off, put our main code, int main. Okay, now we had to start off with what we did last week, working with structs, which, if you guys weren't here last week, they're essentially classes. And so each node has an index, has a range of L, R, and then an attributed value. So that means we need some struct. I'm going to call it node. And then, remember, put the semicolon here. And then we need our left and right. And then an int val, denoting the value attributed to the range L, R. Left and right indices. And then we also said that our segment tree, our array of the segment tree, this was just also another rule of thumb, is that it should have 4 times the array size. So if we have, let's say, int r as 1,000, then we said that our segment tree array, I'm going to call it seg, and it's 4 times. So another rule of thumb that I said is, whatever your array size is, make your segment tree array 4 times the array size. It will prevent any index out of bounds stuff. Okay, so we need to build our tree, and for that we're gonna have to actually get values. So let's say we have n as number of elements in the array, and this is the order they're inputted, and then values, and then each line after has a value in the array. Okay, so that means we need to take our input, and then we need int n, take in n as our input, and then for int I equals 0, I is less than n, I plus plus, cn, and then we called our array r, so we're going to cn r of I, r in index I. And let's just say, because I'm using a maximum size of 1,000, that n is guaranteed to be less than 1,000, just so we don't have to worry about having a variable size array. So first step is to build our tree. So the steps to building our tree are, okay. To build our tree, what we did is we kept dividing the range in half, and then whatever values that we got from the minimum values in each of those, we set our node's minimum value equal to the minimum of the left and the right minimum value. So let's have some function void build tree. And I make it a function because it's going to obviously be calling, it's obviously going to have to call the function more times for the children, and then the children of those children, and then all the way down up until you reach a leaf, or in other words, where L and R are the same. So that means you have to keep calling it, so we want to use a function. So let's call our current index v, and then int, and then now we need to store our left and right. So I'm just going to store them as int left and int right. So let me write those out. V represents the index of node in the tree. Left represents the assigning nodes. Alright, the nodes assign left value. And then right represents the nodes assigned right value. And we know that we have to start off with our root node. Root node has index 1 and has a left value of 0 because we want the root node to cover the entire range of the array, and then a right value of n minus 1. If I could type. A root node has an index of 1, has a left value of 0, and a right value of n minus 1, because there are n elements in the array starting off with index 0, from I equals 0 to less than n. That means the rightmost index is n minus 1. So that means essentially what we're going to do is when we make our build tree method, we want to first call build tree starting index is 1, a left value of 0, and then a right value of n minus 1. Okay, so we're going to go ahead and build our tree now. So first thing to do, first step, assign the nodes left and right values. And that's pretty simple enough. We're just going to do seg, and remember this is index v. So seg at v dot L equals left. So we're setting the current node's index, current node's left value as the left that we got from our function. Seg v, and after that we have to assign the right. Seg v dot r equals right. Now we just assign our current node's right value as the right that we get in the function. And then now we have our left and right assigned. Second step, check whether the node will have children. Obviously you can't, the way we do this is checking whether L and R are the same. If L and R are the same, that means that we're at this current node is not a parent because you can't divide that range in half. The minimum value there, or our value there, is just going to be the array at index L, because that's the left index or the right index. So you could say the values either are at array at L or array at R. They'll be equivalent. So we need to check if L equals R, this node is not a parent node. Oh, not L equals R. Left equals right. Left and right. Because I use left and right as my parameters in our function build tree. So if left and right are the same, then that means our values, our current node's value is just going to be array at L. And option you could also do seg v dot val equals array at right, and not L, but left. Is equivalent. So if this is the value that if left equals right, this is not a parent node, this is a leaf. And so we just assign our seg_v.val equals array at left, meaning we're just assigning it to the array value because there's only one node. So that means the query in the range L, R has to be that array value at the same L or R index, because that's the only one that's in that range. Okay, so if left equals right, we assign our value, and otherwise, we say that we know that this is a parent node, which means that we have to build the two children and assign the current node's value based off of the children's values. Okay, so we have to call our build tree for our two children, and since our left child has an index of v times 2, then we have to build tree with an index of v times 2, and then left, and then we need some middle variable, because obviously we're trying to make the left child have a range of L, left to mid, and then the right from mid plus 1 to R. So that means we have to actually assign a mid value, and the way we can do that is just saying, hey, we just want to make it the average of L to R, not L to R, left to right. So this will be midway between range left to right, found by the average. And then this is obviously rounded down because C++, and since you assign it with int, that means, and since you're doing integer divided by integer, it's just going to return the floor of the division, aka with no decimal, just take the decimal out. So it means we have to build tree from our left to our mid, because now we've found our mid value, so we can just say build tree our left child from left to mid. And then similarly, we have to build our right value, v times 2 plus 1, mid plus 1, comma right. And making sure that I'm not making it mid, comma right, because then you'd have mid in both the left and the right children, which would completely mess up the tree. So this is building the right child. And we're going to stick with building our minimum. Since we're going to stick with doing a minimum range query, that means our seg_v.val, since we're doing minimum, then that means this has to be the minimum of the two values that we get from the two children. Seg of v times 2 dot val, seg at v times 2 plus 1 dot val. Because obviously v times 2 and v times 2 plus 1 they'll always get values eventually, because eventually when you keep building downward and downward and downward, you're going to hit a leaf node. So that means it will be assigned. So that means we can assign a parent's node based off of the two children's nodes, and then use that for the current node's parent node, and then so on and so forth until we get to the root. So this is the way that we build our tree for our minimum range query. Does anyone have any questions so far? Okay, if not, then we'll keep going. Okay, so now we've built our tree, because when we call build tree 1, 0 to n minus 1, then it's going to do all the building using the elements using our left and right of 0 to n minus 1, and then it's also going to use the array elements that we built from our input, and so we pass into array left if we have a children, and it's going to keep building up and up and up. So we're going to so how the tree works is we start with the root, we keep going down from top to bottom, and then and then it builds bottom up until the root. So this is how we build our tree. So now we need to query our tree. So we'll keep querying. We'll actually just keep querying. Let's have a while true loop. QL, QR. And then these will be our query ranges from QL, the range QL to QR. And then we'll take input from them from the user. And then we want to call a query function. Some sort of query function that we have to build. Okay, so I just put in a while true loop so that we can just keep putting query functions as long as we want to. So now we need some sort of query function. And obviously, since we're working with integers in our array and in our segment tree, the values are integers, that means our return type for our query is going to be an integer. Now, we need to store our current index in the tree array, suppose. And then we need our query range left, and then our query range on the right end. Index in array, query left, query right. And then this will return minimum value in range return minimum. Alright, the goal is to return a minimum value. And it's not necessarily going to return in range QL, QR because it has to call its recursive functions. But the end result will be the minimum element in the range QL, QR. Okay, how about I post the cases of the whiteboard that we developed, because we clearly saw that sharing the application is just going to go to garbage and it's not going to work out well. Or no, sharing the screen won't work out well. Okay, so I'm going to post. So I want you to have this open, because if I have it open, it's just going to cause my my microphone to go to trash, because I can't have more than one application open at a time. So cases for seg tree. Okay, so I just posted the cases for our segment tree for a range QL, QR at a node in the tree with a range L, R. So I want you to have that open. Open it, like you can click open and then open original, or just have it somehow with you. Have the cases open with you so that you understand the next part. Okay, so we have our query from index v and then a range QL, QR. So the first case that we said is L, R is completely outside QL, QR. So case 1 is outside QL, QR. And so that means result return huge value, because it is not to be included in the range. So the way we see if L, R is outside QL, QR is if we have a range QL, QR, there are two cases for which the range is completely outside. The right end of the array is less than the left end of the query, or the right end of the query is less than the left end of the node range. Because if let's just look at R and QL first, because let's say R is like 3 and then QL is like 5, that means L has to be less than or equal to 3, and QR has to be greater than or equal to 5, because the right can never be less than the left. Otherwise, the left and right is completely messed up. So that means there's a gap in the elements so that you're not intersecting. And similarly, between QR and L, if we have a value with which L is greater than QR, then that means since we know the right is greater than the left, and similarly the query right is greater than the query left, that means there will be no values intersecting at all. So that means we have to check if the right is less than the query left, or the query right is less than the left. And then in this case, we want to return some really huge value. And notice how I didn't assign R and L, even though in the node structure we had L, R. We had to actually define, and we have to actually make variables for them. So we could just do if seg of v dot right and then seg v dot left. But then you realize that you're going to be typing seg v dot right and seg v dot left so many times that it's just easier to just make L and R variables. So int L equals seg v dot L, and then in the right is R is going to be seg v dot R. So then I can just do if R is less than QL, and then or if QR is less than L. And then we want to return some really huge value. So let's just go 1 times 10 to the power 9, or 1e9. This is just e notation, not the same thing as e the natural log, or e as in 2.718. Not that e, but this is just e notation as in 1 times 10 to the power of 9. So that's case 1. You want to return some huge value, and 10 to the power 9, I'm just going to say is never going to appear in the in any of the elements in the array, so that this value will not be affecting the minimum range query. Now next case is case 2. Let's have a look at it. L, R is inside QL, QR. So in this case, we return the node's stored value. Because L, R being inside QL, QR means that every value, or every index L, L plus 1, L plus 2, all the way to R is valid and can be used. So the way we check this is L and R, L, R being inside QL, QR, that means it has to be such that QL has to be less than or equal to L, so that it holds all the values between, so that you don't want it to be the other way around, because then there's some values between L and QL which are not included. We want all the values with L being including L being inside the range. That means the leftmost point in the query range has to include L in it, or be less than L. So if L is less than, if QL is less than or equal to L, and instead of doing an or, then we have to check our second case. Our rightmost element R has to also be less than or equal to QR, because the rightmost element in our node range has to be included in the range QL, QR, meaning that the query right has to be greater than or equal to the node's right. And both have to be true at the same time. Otherwise, you're going to have some elements outside the range QL, QR. So that means if both conditions have to be satisfied at the same time, we need an AND this time. So QL is less than or equal to L, and R is less than or equal to QR. And then we want to return some node stored value, in which case we do return seg at v dot val. Case 3, final case, L comma R intersects with QL comma QR. Result, check the return values between check the return values of the function with the node's two children, and return the minimum out of the two values that we got, or that we get. And since this is the last case, I'm not going to put an if statement, and so we can just do return the minimum of the query left and the query right. And this looks like now we have to call the query function once again, and then we have to go to the left child, which has an index of v times 2 in the array. Our QL is going to be the same, and our QR is going to be the same. We don't bisect QL comma QR because we're not trying to change the range we're divided into. We have to look for the query of the entire range QL comma QR. We're not going to change that. So that means we can't bisect QL and QR into two different things. So the left and then the right. Query, similar idea. The right child has an index at v times 2 plus 1, and then same range QL to QR. Left and right. So these are the three cases for our query, and then so when we do call our query over here, we obviously want to print it out. Query, we always start at the root, so that means our first v value that we have to put in is 1, and then QL to QR, because those are the variable names that we chose. So yeah, this should work out. So before I test it out, does anyone have any questions or So I do not necessarily believe that all of you completely get this, because it took me a matter of weeks to fully understand this, but we'll just roll along with it. Eventually, I feel like it'll click, or otherwise I just taught it that well, which I don't think I did. But let's try. Okay, so our query range was 4 to 10 from our test thing, and the values are... Okay, so I'm going to test it with the same thing as we used in the example. Okay. So the values are 1, 3, 7, 9, 15, 30, 45. Okay, actually, let me just put the entire sample input. Okay, so there are 12 elements in the array, and there was 1, 3, 5, 1, 3, 1, 3, and numlock isn't working. Alright, 1, 3, 7, 9, 15, 30, 40, 14, 6, and 18. And then we'll just have some cases. Okay, so this is going to be the sample input that I use. And then we'll make cases as we go. It's the same as what we had in our example. 1, 3, 7, 9, 15, 30, 45, 16, 18, 14, 6, 18. Okay. So I'm going to go ahead and paste that into my run thing, making sure that it works. If it doesn't work, oh, I'm going to be mad. Okay. Paste. Okay, so let's go ahead and do, now we'll enter a query from 4 to 10. 6. It worked perfectly fine. And obviously, because we proved in the range 4 to, node 4, and when we were looking at it in our diagram, we saw that the answer, our output was actually 6. So that's good. So range 4 to 10 has a value of 6. And let's go ahead and do something else. Someone give me two numbers between 0 and 11 inclusive.
5.
5 and?
6.
5 and 6. Okay, so we were indexing from 0. So 0, 1, 2, 3, 4, 5, and 6. So the fifth was 30, the sixth was 45. So that means we should output 30. And we do. So, anyone else? You want to just give it one more try? Brianna, I know you had some numbers in mind.
Wait, did you say 0 to 11 inclusive?
Yes. Between 0 and 11 inclusive.
2 and 10?
2 and 10. All right, and so we went from, so that means it'd be including and going up till here. And so obviously, this is out of the indexes range 0 to 2 to 10. And so that means when we put 2 to 10, we should have now put a 6 because it's obviously the lowest element. And we do. Okay, so I think that the segment tree is working perfectly fine. Okay, so, and then we can just keep testing, blah, blah, blah. Well, we found out that it works perfectly, so that's good to hear. Okay, so, now if we look, we've done the minimum range query. But now let's try another wacky thing. Try and do the maximum range query. We need a maximum of the range QL, QR. How can we edit our code? Let's have a look. Okay, so what we did, we need to look at the times that we actually use the min function. So min, we use seg_v.val equals min seg_v times 2.val, comma, seg of v times 2 plus 1.val. So that's the first time we assigned a minimum. Here we did, that was just a comment. And then our final thing, our second thing, is when we return the minimum of the query left and the query right. And then also, when we were looking at our return value for L, R being outside QL, QR, we said that we want to return some huge value as it's not going to be included in the range. So for a maximum range query, there's 3 things that are different in our function. Obviously, first is when we build our segment tree, we want the parent's maximum value to be, the higher of the 2 children's values. So we'd have to do max. The second thing we change is when we're the other 2 things we're going to change is in our query. When we call so first off, if we want to return the maximum out of all the nodes, then obviously this has to be a max, because we're trying to return everything with a target maximum value, and because of that, this 1e to the 9 could actually affect our final result, because if elements are all less than 1e to the 9 and you come across a query range with a value of with values that are outside QL, QR, then it's going to return 1e to the 9, and so that's going to carry up, because if all elements are less than 1 times 10 to the power 9, then we're screwed. If any element is less than 10 to the power 9 as our maximum, then we're screwed. So instead of doing a positive number, let's just return a negative number, because then that's going to be a really low number, and every other element in the array is going to be higher than that, so then this won't affect our maximum. So let's go ahead and actually test this. See if this works perfectly, or as intended. Okay, paste our input. Now if we went from, let's look at 4, 10 again at a different perspective. 0, 1, 2, 3, between 4 to 10. Now the maximum out of all these nodes, or the values, is 45. So if I put 4 to 10, I get 45. Now let's use 5 to 6. Between 30 and 45, I should be outputting 45. And then between the indexes 2 to 10, I should once again be outputting 45. And let's just have something that doesn't have 45 in it. Let's do all of these nodes up here, between 0 and 0, 1, 2, 3, 4, 5. If I do 0 to 5, then obviously the highest number out of all of these is 30, and that should be my output. So 30. So as we can see, the maximum range query is very, very, very similar to the minimum range query. And so, my bad, I just had to drink water pretty badly. So we saw that the maximum and the minimum range queries look very similar to each other. And this is the idea of the segment tree, that you can use it for many different things and not change so much code. But, so yeah, it can be used for maximum, minimum range queries. If you even want to do a sum query from range L from a QL to QR, which is obviously going to be inferior to the prefix sum array, because the prefix sum array, after you do your O of n initialization, then it's just an O of 1 query for a prefix sum array. However, the segment trees will be still O of log n for each query with an O of n of building. So for that specific case, I wouldn't use a segment tree, but it's still doable. Now we have to look at something different. What if we have values and we found a way to do the maximum or minimum range queries, and we can easily modify this to do some sort of query with a left and right range. But what if we had to do something where we had to change a value in the segment tree? Because realistically, in the real world where you use a segment tree, you're not ever going to actually just keep the values in the segment tree array the exact same every time. Some values may change. And we stored our left and right index, left and right range of our segment tree. But there's no way we can clearly index the segment tree array to find exactly where the L, R is in exactly one step. And one hack that you might be thinking of is, hey, when you find the index in the when you get to a point where L, R or left and right are the same, and we assign it to R to left, and you said that equals this node's the node of the segment tree at some index v, you store the index v as holding the spot for array at left, or the index left. And yes, this is one way that you could do it, but it costs another factor of O of n memory, because you have to store the locations of all n elements. So that's one option that you could do. But if you don't want to use any extra headroom, then we can just do something else where we somehow find the location of our segment tree, the location of the node with the property that its left and right values are the same, and its value is the desired value that we're looking for. And when we try to implement this just by checking all 4,000 nodes, for example, it's doable, but not optimal, especially if the size goes to like 10 to the power of 6, which in which the worst case operation is O of n to search for that element, just by looping through each of the things. And it's not sorted, so you can't necessarily do a binary search to find the index, the index which L and R are both a specific target value. But instead, what we can do is, essentially what we want to do is change. Okay, let's update element in tree. So let's say that along with our minimum range query, we're also going to have some times where we're going to get input of some index I in the array, and we want to change index I to be some element v, and then you input it as I v, I space v on one line. On one line, not one line. Okay, so you want to get some index I in the array, change it to be some element v, and have the segment tree reflect all those changes. In other words, when you replace an element in the segment tree, some of the values, some of its parents depended on, well, every parent depends on that value's, that its child's value. So if you look at some node, which has the target L, R being I, because that's the index that we want to modify, we have to go back up and change and look at if all the values of each of the parents are the same and they're correct. Well, they're not necessarily the same. Some may have to change to reflect the changes of modifying one element. So we have to reflect that somehow. And as you could guess, it's just going to be some update function. Void update. Int v, and then, so int v being the index in the tree currently, int I, or let's just call it int idx, and then int val. Not int, int new val. So update, forgot to put comments, update element idx in the array, and change it to new val. The segment tree should be modified to reflect the changes if necessary. Okay, so to do that, we had to first find the node. Find the node with index v. Step 2, change the value of the node with index that we find. And then step 3, modify the tree if necessary. Okay, first step, finding the node with index v. Or index ID, not index v, index idx. So we need to search through the left and the right. And then to do that, we're obviously going to have to store the left and right that we have in our in the current index of the segment tree. So int L equals seg v dot L, and then R equals seg v dot R. Same thing as we did with the query. And actually, what you should realize is we queried from a left to a right in the query method or the query function. Our update function is essentially querying from idx to idx, where the left is idx and the right is also idx. So we're just trying to find where idx is. So we want to use a similar approach to what we have here. So finding a node with range idx, idx, similar to query method or a query function. So we need to find it first. So if idx is less than, instead of using query left and query right, we're just going to use idx and idx because we know that they're the same. So actually it should read, if the right is greater than idx or idx is less than the left, that means that case 1, idx is outside the range L, R. And here we don't want to do anything. This is useless. This this search won't yield anything. Then we just want to return get out of there. That's not helping us at all. Case 2, idx is in the range, or case 2, idx has been found. And that can be seen by left and right being the same. And then at the same time, left and IDX are the same. Because if left and IDX are the same and left equals right, that means left, IDX, and right are all the same. And then we found the node with index v. We found the required node to modify, actually. So we need to modify node. And then third step, IDX is in the range L, R, but L and R are not the same. And this is going to look like if L is less than or equal to IDX and IDX is less than or equal to R. So it's inside the range. Then we have to check two children and modify. We need to modify and update the tree here. So first, if left equals right and left equals IDX, we need to modify the current node because we found it. And since that is going to have only one element that's in the range L, R, then we can just simply update it. Seg v val equals, and then the new val we need to put in. New val. Seg v val equals new val. And then once you do that, you need to just return. Get out of there. That's useless. We don't need to do anything now. And then after, what's going to happen is, so what happens is, you're going to go to case 1 sometimes, but most of the time when you go to case 3, where IDX is in the range L, R, you have to divide it, you have to check each of the children, and you're going to keep checking each of the children. Sometimes you're going to run to the case 1, where it's outside the range. Sometimes you're going to run into a case, other times you might run to case 3, where it's in the range, but not, L and R are not the same. But there's going to be one moment in which you find that, you have exactly one thing where you find that left and right and IDX are all the same, and that's the node that you update. So that call comes from this dividing the node in this checking, in this case where you check each of the children. In which case what you have to do is call the function on the children, first of all. So that means you'd have to call update. Left child has index v times 2. IDX is still the same, and new val is still the same. And then update the right child. IDX, new val. And here, one of those calls is eventually going to lead to finding the correct element. Correct node to modify. And here, so that means the current node here is a parent or an ancestor. And what an ancestor means is it's not necessarily a parent, but if you kept going up, the node's parent, and then its parent's parent, and then it's that node's parent, you're going to keep going up, and you're going to eventually find that the current node here with index v is an ancestor of the node we modified. In which case, that means we might have to modify this node. So that means now, not modify, but we have to update update tree at this node. In which case we would just do seg v dot val equals max, and since I changed everything to max, we're just going to stick with max. Seg v dot val equals max of seg of v times 2 dot max, no, dot val, comma, seg of v times 2 plus 1 dot val. Resetting the max value. Or updating max value will change if it actually I don't want to say will change if it actually changes, but if it actually is needed. And so what's happening, so let me explain this one more time. We call the function on the children, and since we call the function on the children, and eventually one of those calls is going to reach the case 2, that means since we called it from here, that means this current v value that we have when we call the 2 children is going to be some ancestor to the range, to the node that we have updated completely. Or that we have updated seg_v.val equals new val. So that means that this is an ancestor, and to essentially make sure that, to guarantee that this has the correct value, or the updated value if necessary, this will be updating we just call it the max query out of the 2 children. And so first it will actually change the node, and then that node's parent will be updated via this, and then that node's parent will be updated via this, and then keep going all the way up until you get to the root. So this is our update function. It's slightly more confusing, I would say, than the query function, but it's quite similar. We see that we did, we checked if it was completely outside the range, that it's completely inside the range, and that we did something with the maximum of the 2 queries, of the 2 children. And so we did something here. Check if it was outside the range, check that it was inside the range, modify the value, and then assign the value that we get to the maximum of the 2 children to our current node's maximum value. So they're quite similar in structure. But yeah, any questions about the maximum range query? Yes, as Kevin said, the query function is more confusing. Okay. So yeah, this is probably a lot of information to digest. But yeah, let's actually check if this works first. So let's have the same elements. Paste. Actually, no, we have to actually modify our code to even take a maximum range. Actually, we won't test that. It looks like it looks good, so we won't test that because you have to modify a lot of code. You have to modify a lot of code down here for it, and it will get shaky. I'll make a problem to make sure that this works, and I'll test the code out and everything. All right. So if no one has any questions, I don't want to do lazy propagation. That's gonna. If you don't know what that is, it's when you constantly update, it sometimes takes a lot of time, and what lazy propagation allows you to do is keep waiting, procrastinate on the update essentially until you need to call the update function on, or you need to call some query function on that child. But yeah, I think I'll save that and maybe make that lesson later on. But this should be some good practice with the segment tree. And first off, I can't believe that no one's asking any questions, because it is, in my opinion, a concept that when it clicks, it makes so much sense to use, but it took so much time. It takes so much time for some people to click, as I've seen in the past. But maybe you guys are all geniuses. And that's good to hear.